Hi, how's it going, guys? Today we're going to be going over Gaussian elimination. Or in other words, we're going to be going over how to solve a matrix or solve a system of equations with a matrix. So Gaussian elimination is a formalized process of using matrices to eliminate two of the variables in each equation in the system. This results in an easy way to find the solution set. The process involves using elementary row operations to generate equivalent matrices that lead to a solution. So the elementary row operations, they are multiplying a row by a constant or adding two rows. And when you add two rows, you're going to replace the second row that you're adding with the sum of the two rows. So for instance, if I have row 1 and row 2 and I add them together, so I'm adding row 1 with row 2, the sum of these two rows is going to replace my row 2. And you're going to see an example of this in the next slide, but that is what that elementary row operation is. Leading coefficients, they are the leftmost non-zero element of that row. If you look at this matrix A over here, the leading coefficient of the first row is going to be 2, since that's the first non-zero number in that row. The second row will be -4, the third row will be -2, and the fourth row will be 8, since those are all the very first non-zero number in those rows. So the point of Gaussian elimination is to get us to a matrix like this. The two things to pay attention to in this matrix is the diagonal. You see the diagonal here is all ones. That's what we want. And also what to pay attention to is that everything underneath that diagonal is zeros. Or in other words, the bottom left corner are all zeros. So with that in mind, there's also, before I go on, there's actually something called a Gauss-Jordan elimination, and that gets us to this point right here. This is just for general knowledge. A Gauss-Jordan elimination reduces a matrix as much as possible, and we see the only thing we have in this part of the matrix is just your diagonal of ones, and everything else is zeros. That is the point of a Gauss-Jordan elimination. And a Gaussian elimination just messes with the bottom half, or the bottom half of the diagonal. Okay? Anyway, let's stop talking about it, actually look at a problem, look at how to solve it. So here we're going to be solving a system of 3 equations with 3 variables using Gaussian elimination and then back substitution. So the very first thing we should do when we have a system of equations like this, what I like to do is I like to look at my equations and see which one has the coefficient of 1 for the x value, right? And that's because if I don't have a coefficient of 1 for the x value, I'm going to have to divide that whole equation by whatever the coefficient of x is to get it to a 1. Because remember, if you go back and look at the Gaussian eliminated matrix over here, the coefficient of the very first variable, or the very first entry in the matrix, has to be 1. So if I go back to my problem, if I kept it as is right here, and I put this into a matrix, I end up getting 2, 3, 2, -3, 1, 1, 1, 0, -1, 2, -3, and -1. So I'll have to turn this 2 into a 1, and I'll do that by multiplying the row by 1/2. And if I do that, I'll end up getting, you can divide everything by 1/2, or divide by 2, I'll get 1, 3 over 2, 1, -3 over 2. If I multiply everything by 1/2 to get the coefficient here to be 1. And in that case, I'm going to have fractions. You'll still get the right answer doing it this way, but using fractions is a pain. We don't want to do that if we don't have to, right? So instead of solving it like this, what I'm going to do is I'm going to rewrite my system of equations, and I'm going to put the second equation as my first equation in the system of equations, because the coefficient of that x is 1. So I end up getting x plus y plus z equals 0. I'm just going to flip these two. So my second equation becomes my first equation. My first equation becomes my second. So 2x plus 3y plus 2z equals -3, and x, or negative x, sorry, plus 2y minus 3z equals -1. So I'm rewriting my system of equations to put it this way. It's perfectly okay to do this. All you're doing is changing which equation is in which order. It's not changing anything. It's not going to change the answer. This is perfectly okay. What you put as a second and third equation, it doesn't really matter all too much or really at all. The most important thing is to make sure the very first equation in your system of equations has a coefficient of 1 if possible. You won't always have this case, but if possible, do it like this. It will make your life much, much easier. So now we're going to take the system of equations, we're going to put it into a matrix. So we're going to use all the coefficients and put them into a matrix. So the first row becomes 1, 1, 1, 0. The second row becomes 2, 3, 2, -3. And the third row becomes -1, 2, -3, and -1. So now that I have my matrix, my system of equations, and I see my very first coefficient here is a 1, that tells me that I'm ready to start eliminating stuff and using Gaussian elimination. So rewrite that real quick. So when you're doing Gaussian elimination, how you want to work it is you want to work kind of in an L. So the very first thing we want to eliminate is this 2. We're going to end up now because we need the 2, the -1, and the 2 to all be zeros. We're going to work one at a time, and the very first thing we're going to try to get rid of is the very first 2 over here. So I'm going to use the first equation, and I'm going to multiply the first equation by -2. So -2 times row 1 plus row 2, and the sum of that is going to replace my row 2. So -2 row 1, what that gives me is -2. So it's -2 times 1 is -2. -2 times 1 is -2, and -2 times 1 is still -2. So that's what my -2 R1 is going to be. I'm going to add that with R2, just regular row 2. Row 2 is 2, 3, 2, and -3, right? I'm just taking the entries of each matrix, putting them to the side, and I'm going to add them together. So I'm going to add them in columns like this. So -2 plus 2 is 0. -2 plus 3 is 1. -2 plus 2 is 0. And 0 plus -3 is -3. So this right here is my new row 2. So let's go ahead and rewrite our matrix with our new row. So the very first row is 1, 1, 1, 0. The second row is what we just solved for, 0, 1, 0, -3. And the third row is -1, 2, -3, and -1. The first row and the third row are still the exact same. We didn't mess with it. The only thing we changed was the second row. So let's keep going. Now we need to get rid of that -1, right? Because we need that to be 0. We need everything underneath the leading coefficients of the diagonal to be 0. And to get rid of that -1, if I look above it, the only thing I can really use is this 1 over here. So that's what I'm going to use. So to get rid of that, I know I just need to add the two equations together, since 1 plus -1 gives me 0. So I'm going to do row 1 plus row 2, and that's going to replace my row, or I'm sorry, not row 2, row 3. Row 1 plus row 3 is going to replace my row 3. So row 1 is 1, 1, 1, 0. That's my row 1. And my row 3 is -1, 2, -3, and -1. And I'm going to be adding these rows together. 1 plus the -1 is 0. 1 plus 2 is 3. 1 plus -3 is -2. And 0 plus -1 is -1. So this is my new row 3. So let's go ahead and rewrite our matrix again with our new row 3. Row 1 is 1, 1, 1, 0. Row 2 is still 0, 1, 0, negative 3. And row 3 is now our new row we just solved for, 0, 3, negative 2, and negative 1. So now I see that with this new matrix, everything underneath this leading coefficient is 0, and that tells me I'm done using my row 1. Okay? If I try to use row 1 to delete the 3 that's over here, I'm going to end up adding that 1 that I circled in green with the 0, and I'm going to change that 0 back to a 1 or back to another number that I don't want. So that tells me if everything underneath the leading coefficient is 0, you're done using that whole row. Leave it alone. You're not going to get anywhere. You're going to be working backwards. So now that I'm done with my row 1, I'm going to go on to row 2, and that's the row I'm going to use to get rid of that 3 that I need to get rid of, right? Because that's the last thing I need to get rid of. And I'm going to use my row 2 to do so because row 1, like I said, is going to get rid of that 0 if you do that. So I'm going to multiply row 2 by negative 3. Since I multiply by negative 3, the number above the 3 in that third row becomes a negative 3, and negative 3 plus 3 is 0. I'm going to add that with row 3, and that's going to replace my row 3. So let's go ahead and multiply. Whoops, there we go. Well, I'm going to go ahead and multiply row 2 by negative 3. That gives me negative 3 times row 2 gives me 0, negative 3, 0, positive 9. And row 3 just gives me 0, positive 3, negative 2, and negative 1. I'm going to be adding these together. So 0 plus 0 is 0. Negative 3 plus 3 is 0. 0 plus negative 2 is negative 2. And 9 plus negative 1 is positive 8. That's my new row 3. So let's go ahead and put this into our equation again. The first and the second row stay the same. We didn't do anything to them. And my third row is what we just got. 0, 0, negative 2, and 8. So all that's left is to make sure that the diagonal is all 1, since we have zeros where we need them to be. All that's left is to change that negative 2 to a 1. So what I'm going to do is I'm going to multiply row 3 by negative 1/2. And that will replace my row 3. So if I do that, the first row stays the same. The second row stays the same. It's supposed to be 0. And row 3, we're going to multiply each value in that row by negative 1/2. 0 times negative 1/2 is still 0. 0 times negative 1/2 is also 0. Negative 2 times negative 1/2 gives you a positive 1. And 8 times negative 1/2 gives you negative 4. Now I see that I have my Gaussian eliminating matrix, right? The diagonals are all positive 1s, and everything underneath the diagonals, everything underneath the leading coefficient is 0, or in other words, this bottom left corner is all 0s. So what I'm going to do now is something called back substitution, which is a fancy way of saying plug your values in backwards. So we just take this matrix and take it out of our system, matrix and put it into a system of equation. The first row tells me x plus y plus z equals 0. The second row tells me y equals negative 3. And the third row tells me z equals negative 4. So I see I have my z value, and I have my y value. All I need to do is plug these back into the first equation, and I'll have my x value. So we know x plus our y value, which is negative 3, plus our z value, which is negative 4, is all going to equal 0. Negative 3 plus negative 4 is negative 7, so x minus 7 equals 0, or x equals 7. And that's my x value. So I also have my y value and my z value. So I can go ahead and just rewrite my equation, or sorry, my numbers into an ordered triple. So it's 7, negative 3, negative 4. And this will be my final answer. Remember, you need it in an ordered triple. So let's go on and do problem 2 as well over here. We're told 4x minus 3y plus z equals -8, negative 2x plus y minus 3z equals -4, and x minus y plus 2z equals 3. So again, first thing I'm going to do is I'm going to swap my last and my first equations because I don't want to deal with fractions. I would have to divide the whole first row by 4, and I'll end up with a -3/4 and a 1/4 somewhere in the matrix, and I definitely do not want to deal with that. So I'm gonna swap my first and my third equation. Sorry. So my first equation becomes x minus y plus 2z equals 3. My second equation stays the same. Negative 2x plus y minus 3z equals -4. And my first equation becomes my last. 4x minus 3y plus z equals -8. And I just want to say again that your second two equations right here, you can swap these if you want to. It really doesn't matter. The most important thing, like I said in the first on the previous slide, is to make sure your coefficient of x is 1, because it will make your life so much easier if it's like that. So let's go ahead and take our system of equation, put it into a matrix. The first row tells us we have 1, -1, 2, and 3. The second row tells us -2, 1, -3, and -4 are entries for the second row. And the third row will be 4, -3, 1, and -8. It's a really big matrix. There we go. So that's what our matrix is for this system of equations. So like the previous slide, what we're going to do is delete the entries in the matrix in an L shape. So we're going to get rid of that -2 first. That's the first thing we're going to worry about. And we're going to use the leading coefficients of the diagonal, the first diagonal, to do so. Or in other words, we're going to use row 1 to delete these two entries here. Okay? So to get rid of that -2 first, we're going to multiply the first row by -2. So -2 times row 1 plus row, not -2, but +2. So it's 2 times row 1 plus row 2. That's going to replace row 2. So let's go ahead and figure out what that's going to be. 2 times row 1 gives us 2, -2, 4, and 6. And row 2 gives us -2, 1, -3, and -4. We're going to add these together, and we're going to see what we get. 2 plus -2 is 0, just like we expected, just like we wanted. -2 plus 1 is -1. 4 plus -3 is 1. And 6 plus -4 is 2. This is our new row 2, right? So we're going to go ahead and rewrite our matrix and put that in. The first row stays the same. We didn't change it. The second row, we did change into this 0, -1, 1, and 2. And the third row, we didn't change it. 4, -3, +1, and -8. So we got rid of the number right here. We got a 0 over here that we wanted. Now we need to get rid of that 4. So to do that, we're going to multiply. We're going to use the first row again. So we're going to multiply the first row by -4. And we're going to add that to row 3. And that will replace your row 3. So -4 times the first row gives us -4. -4 times -1 is +4. -4 times 2 is -8. And -4 times 3 is -12. We're going to add that with row 3, which is just 4, -3, 1, and -8. We're going to add these together. -4 plus 4 is 0. 4 plus -3 is 1. -8 plus 1 is -7. And -12 plus -8 is -20. This is our new row 3. let's go ahead and put it into our matrix. Our first row didn't change. It's still, let's see what it is, 1, -1, 2, and 3. Our second row is still 0, -1, 1, and 2. And our last row is now 0, 1, -7, and -20. Right? This is our new row 3, and that's what we did. Okay, so we have one last thing to eliminate, and that's this one right over here. And since everything underneath this leading coefficient here is 0, everything underneath is 0, we are not going to use row 1 anymore, because if we use it, we're going to change those zeros. We don't want to do that. So what I'm going to do instead is I'm going to use row 2, and I'm going to add it to row 3. So row 2 plus row 3, and that's going to replace row 3. And that's because if I add these together, I see the negative 1 here added with the 1 over here is going to be 0. So I can get rid of that 1 like I want to. So row 2 is 0, -1, 1, and 2. Row 3 is 0, 1, -7, and -20. I'm going to add these up. I get 0 plus 0 is 0. -1 plus 1 is also 0. 1 plus -7 is -6. And 2 plus -20 is -18. And that is my new row 3. So let's go ahead and rewrite our matrix and let's see what we get. The first row stays the same, 1, -1, 2, and 3. Row 2 is 0, -1, 1, and 2. And the third row, we just changed to 0, 0, -6, and -18. Let's rewrite that to a better looking -18. There we go. So all that's left now, we have the zeros in the bottom left corner. All we have to do now is change these into 1s. So to change -1 into a 1, I'm going to multiply row 2 by -1, and that's going to replace row 2. And I'm going to multiply row 3 by -1/6. And that's going to replace my row 3. So let's go ahead and change our matrix accordingly. The first row stays the same, 1, -1, 2, and 3. My second row, we're multiplying everything by -1. 0 times -1 is still 0. -1 times -1 is 1. We get -1 there, and a -2 here if we multiply it all by -1. We're going to multiply the third row by -1/6. 0 times -1/6 is still 0, so our first entries are 0. -6 times -1/6 gives us a +1. And -1/6 times -18 gives us a +3. So we have our diagonal. Our diagonal is all 1s. Our bottom left corner is all 0s. And so all that's left to do is put this to a system of equation and solve for our x, y, and z. So the first equation, or sorry, the first row tells us x minus y plus 2z equals 3. The second row tells us, sorry, not x, but y minus z equals -2. And the third row tells us z equals 3. So we know what our z is, so all it's left to do is use back substitution or just plug everything in backwards. So we're going to plug z into our second row. So we get y minus 3 equals -2, or y equals 1. So now we have our y and we have our z. We're going to plug that into the first equation. So we're plugging what we got into the top equation now. So we have x minus our y, which we said is 1, plus 2 times our z, which is 3, or 2 times 3, or 6. And that equals 3. -1 plus 6 is +5. That equals 3, or x equals -2. So now we have our x value, we have our y value, and we have our z value. All that's left is to put it into an ordered triple of -2, 1, and 3. And that is our answer. So there's one more example. You guys can work it on your own, and you can use Photomath or some other app or Google, whatever you want to use to get your answer to see if you got it correctly. So you can pause the video and try it if you want. And at the same time, there's these two homework problems. If you're watching before the homework is due, make sure you do it and have it ready by Monday. And if not, these are still very good problems to do and practice on to make sure you understand how to use matrices to solve our system of equations.